So the last day we looked at this idea that this diagonal square, the area of this diagonal square, well, we can chop it up and find the area this way, but it looked like that this triangle and the inside of the square, when we look at it on the outside and take a look at the squares from the sides of those triangles, it seemed like those square areas added up to the area in the diagonal triangle. So we see this with this formula, a squared plus b squared equals c squared. Well, we're not sure if this actually works, so let's just check to see if this is actually working. So if we take a look at this diagram here, we can see that we can count, okay, that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the area of one edge is going to be 10. So side A is going to be 10. And if we count B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's also 10. Okay, so this is a 10 by 10 triangle. And we can make 10 by 10 triangles inside there. So the area of side A is going to be 100 when we square it. Side B will also be 100. And when we count up the area of side C, okay, so let's see here, so it's going to be 10 by 10 divided by 2, so 50, 50, 50, 50. So the area of side C squared, when I add up that triangle, appears to be 200. Okay, and so the length of side C is square root of 200, which is approximately 14.14. Okay, so we want to see if this relationship actually holds true. Does this area in here, this A square area and B square area, those two red areas add up to the blue area of C squared? Well, when I add those two areas up, A squared and B squared, yeah, we do get 200 squares. Okay, so it appears that this relationship is holding true for this first triangle. Okay, so maybe we just got lucky in all these triangles that we've been trying. So we'll try one more. Okay, so here's another one. This one's not, it's got a square in the middle, so it's not symmetrical. So maybe it's the fact that it was symmetrical that allowed it to work. So we're going to count up these areas of A and B, so A square and B square. So its length of side A looks like it's 1, 2, 3, 4, 5, 6. So side A is 6 units. So A square, there's 36 squares in that square there. Okay, we'll just write that in, 36 squares. Length of side B is 1, 2, 3, 4, 5, 6, 7, 8. So B square is 64 squares. Okay, so there's 64 squares in here. And when we actually add up these areas in here, well, we have 4. Okay, this is a 8 by 6, so 8 times 6 divided by 2 is 24. All these triangles are exactly the same. So when I add up all those areas, I end up with C squared equals 100. So length of side C is 10. And so the relationship here, does this relationship hold true? A squared plus B squared, 36 plus 64 equals 100. Okay, and it seems like this is working. Now, it's important to recognize that the relationship seems to be with 3 areas. Okay, it's nothing to do with the side lengths, because 10 plus 10 does not equal 14.14. Okay, the side lengths, there doesn't seem to be a relationship. But there seems to be a relationship between the 3 areas, the 3 squares. So here's the same thing. There doesn't seem to be a relationship with the side lengths. 6 plus 8 does not equal 10. But this square and this square seem to add up to that diagonal square. So based on this, it appears that the two square areas off of A and B, so A square plus B square, seems to add up to the triangle off the diagonal triangle C square, the diagonal square. So those 3 squares seem to be connected somehow, and it appears to be true. And this is what we call the Pythagorean relationship. Now, this seems to be very true. We have not yet proved it. We haven't shown any kind of proof of this, but it certainly seems like the relationship is there. And the relationship is with the areas, with the three squares, not with the side lengths, but with the three squares. They seem to be related. They're connected to each other. So what I would like you to do is come up with your own. Okay, so I'm going to draw a random triangle here, right triangle. Now you need to choose something different than mine, but I'm going to maybe go 4 this way, and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go 4 and 9. Okay, and I'm going to connect that diagonal here. Okay, so there's my right triangle. I'm going to use that 4 and 9. So I'm going to 1, 2, 3, 4, 1, 2, 3, 5, 6, 7, 8, 9 to get the corner. Okay, so be very careful of how to count up the coordinates to get the corner. So it's good. We're going to switch to X and Y. Okay, make sure you count accurately. So I'm using 4 and 9 to get the corner. So I'm going to use 9 and 4 this time. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. Okay, and notice that triangle, I could have drawn it the other way. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Either way, we're going to get that corner. And that corner allows me to generate the square. Okay? And you can see now that if I kind of draw in these lines here, you can see the triangles that make up that square. It's going to be the same as this right triangle here. I'm just going to highlight it. Okay, this is my 4 by 9 triangle. And that same triangle shows up on the outside there. Okay, so the relationship that I'm looking for here is the square off of this side. So this is going to be a 4 by 4 square. So that's a 16. There's 16 squares here. And this is going to be a 9 by 9. So 2, 4, 6, 8, 9. Okay, so this is going to be, actually I should do this in red since it's down below the colors are red. Okay, so here's my 4 by 4 square. Here's my 9 by 9 square. Okay, so this is going to be 16 and 81. So this is going to be 4, 9, 16 squares, 81 squares. And we are getting 97 squares in red. Okay, so we want to see that the C square is going to add up to 97. Okay, so let's count this up. This is going to be 4 by 9 divided by 2 is going to be 18, 18, 18, and 18. Okay, the square in the middle is going to be a 9 minus 4 square, or a 5 square, or 25. Okay, so let's add that all up. So we get 36, 72 plus 25. Yeah, there's 97 squares in that black square there. So C squared is 97. Okay, these are equivalent. Okay, the length of side C works out to be square root 97. Okay, it's just a little bit less than 10, so 9 point something. And again, notice that these two side lengths, 4 and 9, do not add up to 9 point something. Okay, the side lengths are not related. What's related is, and the picture kind of shows that, is that these three areas are connected to each other. This square and this square seem to be able to fit into that square. And that's what our Pythagorean theorem is saying. Okay? And again, this is not anything like a proof. Okay, we haven't proven this, but it certainly seems that a squared plus b squared equals c squared. It seems like it works. So we're going to start using this calculation to help us with these areas. And we can find these areas, but more importantly, what ends up happening is we can use these areas to find these three side lengths. Okay, now we need to still square root. Okay, we need to go from area to side length to be able to do that. But this now allows us to find these lengths of these sides. In particular, the length of this diagonal line, which is not a very easy number to get. Okay, because for one thing, it's that diagonal. We can't count along the grid anymore, and it's it's not necessarily a nice number to calculate. Like in this case here, square root 97 is a really, really messy number. But this relationship allows us to calculate that length of that side.